Welcome to IMV Imaging Academy series. I'm Natalia, from Animal Imaging Marketing Director. Today we are talking about the use of the ultrasonography on swine reproduction in the field. I'm delighted to welcome Dr. Carlos Henrique Cabral, Professor in Reproduction at the Pontifical Catholic University of Minas, Gerais, Brazil. Dr. Cabral has wealth of the experience in animal reproduction, semen and embryo technology in domestic animals. His focus is on swine production and artificial insemination. Today's webinar has been pre-recorded, so there will not be opportunity for questions and answers session. There is an email at the end of the webinar if you would like to get in touch with us and send us questions. We now welcome Dr. Cabral.
Thank you for presenting me. Good afternoon for you all. It's a pleasure to be here and attending this invitation of IMV Imaging. And we are going to talk a little bit about the use of ultrasonography on swine reproduction in the field. I think you all know that fluxogram, and here we have the most important index when we talk about pig production. It's pigs sold per sow per year, that in Brazil the minimum number of pigs sold per sow per year is around 25 to 26 pigs. Under this, the producer won't keep in the activity. To get this number, we must win around 11 piglets per farrowing, and to get this number of piglets per farrowing, the producer has to have must have a total of 13 to 14 piglets born alive, or total born, sorry. Well, ultrasound will help us to maximize the productive days and minimize the unproductive days, especially. And we will do that decreasing the infertility diagnosis failure. Ultrasound can help us as well to monitor the index and the issues that will lead us to have good index, considering the number of weaned piglets per farrow. Well, ultrasound, using ultrasound, you give us information. It's very important to know what we are going to do with this information. The machine, the technique can help us giving us information, but we have to know how to handle with this information in order to improve our indexes in the herd. The most used reason for ultrasound in a herd is the early pregnancy check. According to our experience, we can properly diagnose gestation with 19 days of gestation. The sensitivity during the examination these days is around 90%. So it means that in 90% of the case that the sow is pregnant and we give this diagnosis, we will be right. Well, when we are not so sure, so comfortable to say that the sow is pregnant on day 19 of gestation, how we act? We ask for the keeper to pay much more attention in this sow in the next days, because probably it's going to show estrus in the next day. So we can help the keeper to find sows that repeat the estrus and has to be inseminated again. So this way we can decrease the non-productive days. Another recommendation that we give is to repeat the examination each 15 days until the day 90 of gestation, to know approximately the period of gestation losses. For example, if we know in each interval the sow is losing the gestation, we can have information to suspect of some special disease, and this information can be compared to serology, for example, and other results, other information that the veterinarian will have to diagnose this disease, and then to be more precise on trying to take off the influences of this disease of the herd. We can suspect of estrus detection failure. We can suspect of some stressors that is happening and that are happening we cannot see. So we can decrease the non-productive days. Another possibility of diagnosis infertility is we can talk about an experiment that we published last year that we named Inaccurate Assessment of Reproductive Status Leads to Unnecessary Removal of Cycling Sows. So what we did, we followed 115 sows culled for reproductive reason, and we examined the ovarian status at the slaughterhouse, where we could see follicles of several sizes, corpora lutea, corpora albicans, and ovarian cysts that should justify some reasons of culling. We follow also the uterus, where it could diagnose endometritis, and the bladder, where we could find cystitis. After all the examinations, we compared our findings with the farm record, and what we could see was very surprising. Only in around 20% of the cases, the findings were in agreement with the culling rate, the culling reason, sorry. So sows code for low productivity had ovaries devoid of follicles. It could be a problem of an estrus or corpora lutea that shows that the sow didn't have a reason for this low productivity, or cystic ovaries and endometritis, telling us that this sow was submitted to stress or to contaminated semen. Well, if we had this information before culling these sows, we could try to keep these sows at the herd, giving them the attention or the treatment to keep these sows at the herd. Nowadays, the genetics are getting more and more expensive. The welfare strategies tell us to keep the sow in good conditions, that they can be treated and not suffer by these reasons. So ultrasound gives us information, and we will decide what we will do with this information. So another information is about the ovary situation. For example, we can detect ovulation in sows using ultrasound. It's especially important when we use fixed time artificial insemination program, when we are going to implant this program, to know where the sow is ovulating along the estrus. It's very important because when we implant a program like this, a fixed time artificial insemination, we will use ovulation inducer, that is a hormone, and I have to check if the ovulation is taking place at the right time that the technology of inducing ovulation tells us that it's going to happen. If I am sure that the ovulation will occur at this time, I can inseminate before ovulation at the right time. When we are implanting a program, we are not completely sure if the employees will apply the hormone injection at the right time, if we will do all the preparation to use the hormone okay. So identifying the ovulation, the moment of ovulation, or the interval where ovulation occurs, will give us an idea, a precise idea of where, of what is the interval of insemination to ovulation. And it will guarantee the results even using only one insemination or using frozen semen. If you use only one insemination, that is very important nowadays, because we have to take advantage of the boars with better genetics, and we have to use an ejaculate in the a lot of sows. So we have to decrease the number of viable sperm cells per dose, and we have also decreased the volume of the extender by insemination. If we decide to use only one insemination, we have to be very precise of the interval between ovulation to insemination to ovulation, sorry. And we have to guarantee that this interval won't be longer than 24 hours. Using frozen semen, it's more delicate because frozen semen has a decreased viability after thawing that we suppose it can be in a minimum 4 hours and not more than 12 hours. So we can do that like they do in horses, that to guarantee the results, they inseminate just after ovulation. So depending on the situation, especially when you import frozen semen for form a herd here in Brazil to multiply genetics. This semen doses has a very high value, and you have to take advantage of them the more you can. So you have to guarantee the farrowing rate and the litter size. So knowing where ovulation is going to take place is very important in these situations. So let's talk a little bit about the physical principles of ultrasound. Well, ultrasound is based on the echo. That's why it's called also echography. So we know that the sound travels through the medium depending on the density of this medium. The energy, the sound energy passes through the molecules from one molecule to each other and so on. So it's like it is propagated. So depending on density of the medium, we can calculate or we can know the speed of the sound. So if I emit a sound and this sound meets an interface, it will reflect, depending on the acoustic impedance of this interface, it will reflect and it will come back to the emitter that will recognize this sound. So what ultrasound technologies do is calculate a distance. For example, if I know that the speed of the sound is 343 meters per second, and it took 1 second to go to the interface and to come back to the emitter, I can suppose that the distance from the emitter to the interface is the half of 343 meters, that is 171.5 meters. So all ultrasound do is calculating a distance. We use the concept of some abilities of some animal species. They are of a group of fishes, and so they can know exactly on where the fishes are. And in group, they make a strategy to get to this group of fishes and to get them. Because in the water, as the density of the water is much higher than the air, for example, in the air we can see in long distances, but under the water we cannot. Even the dolphins, they cannot. So the ultrasound system that they use is very important to calculate a distance from them to the group of the fishes. And most important yet is how the bats make the space orientation, because they cannot see. So they use a ultrasound system. They can emit ultrasound waves, and they can capture these waves, the echoes of these waves, and how they can to orientate in a space and fly around without beating any obstacle. So knowing about the transducers, what kind of transducer we have? We have two kinds of images. The angular image that is produced by the sectorial or convex transducers, and the square image that is produced by the linear transducer. We will use almost all in all the situations the sectorial or convex transducer to do our job, working with sow swine female reproduction. But the linear transducer can be used as well to examine the testicles of the boars or to examine the carcass of the animals. But we won't discuss these issues here. Well, let's learn a little bit about sound propagation. The speed of sound is determined by the mechanical compression wave transmitted from a molecule to each other. So it's what we already told in some of the slides we just saw. It tells us about the density of the tissues. The closer the molecules are, the greater the ability to propagate a wave of pressure, the higher the speed of propagation. So it's the principles of sound emission that we have to know. What is ultrasound? It's a term given to sound frequencies above the ones detected by human ear. Human ear, for example, can detect sound frequencies that vary from 30 Hz to 20 kilohertz. Ultrasound images for medicine diagnosis vary from 2 megahertz to 25 megahertz. Let's understand a little bit better this. What is frequency? It is the number of complete cycles that happens in 1 second. 1 cycle per second is defined by 1 hertz. Hertz is the unit to measure the frequency. 10 cycles per second is 10 hertz. How is ultrasound generated? So applying electrical pulses at piezoelectric crystals, what does it mean? Piezoelectric. It's the capacity that the crystals have to transform electricity to sound energy, and the opposite, to transform sound energy to electricity. So when we apply these electric pulses to these crystals, deformation by compression and return to original state occurs. If we apply electrical pulses 1,000 times per second, crystals will generate ultrasound waves with the frequency of 1,000 cycles per second. That is 1 kilohertz. If we apply 5 million cycles per second, it means a frequency of 5 megahertz. How is image generated? The transducer emits short sound wave pulses that hit tissues of different impedances and return to the transducer, compressing these crystals. When ultrasound waves return to the transducer crystals, deformation occurs, and as a result, there is the production of an electric pulse. This electric pulse, is converted to digital sign, and it's interpreted as a monitor image. So the image processor has the function of transforming the echoes that comes back in electrical signs in image. So here we are going to have a notion of the tonalities or the color in ultrasound monitor, considering the density of the tissues that is related to the speed of the sound in the tissues, and as a result we have an index that is impedance, acoustic impedance. So as media we have here air, water, blood, muscle, and bone. And it's very, very important to notice the difference between the density of air and water in grams by cubic centimeter. When we compare the different density between water, blood, and muscle, we can see that they are very, very similar. And when we compare again these densities to the bone density, that is a solid matter and has much, much less water than muscle in his composition, we can see that the difference in the density is very high as well. So how it is showed up in the monitor, in the monitor of an ultrasound machine. The ultrasound machines for medicine are calibrated to a water medium because the tissues have a lot of water in their compositions. So the water represents a black, a completely dark brightness. And blood, as we can see the difference in the impedance, has a gray color, but it's a dark gray when we compare it with muscle. That is a little more dense, as we see here, and it's a less dark gray compared to the blood and to water. When we look at the brightness of bones representing the image, we can see a completely white brightness. It's because most or the total sound that reaches the bone is reflected to the transducer. The less the impedance, the less the sound will reflect in this medium. The more the impedance, the more the sound will reflect in this medium. So we cannot see inside the bone because all the sound will be reflected in the surface of the bone. And when we look at the air appearance in the ultrasound machine monitor, we can see that it is represented for a white color as well. It is because the difference in the impedance of the air and the water is very, very high. So the speed's difference is very high as well. So as the calibration of the apparatus is for liquid medium, this energy that heats the air surface or the surface that have air inside, the air gets back to the transducer in a very, very different speed, so it cannot be interpreted by the ultrasound machine. So most of the energy gets here, and it's represented by a white color. Okay, let's try to explain it in the image. I think it will much better to understand. So here we have a transducer. The crystals of the transducer are in the surface, or the almost in the surface of the transducer. This is the cable that brings the electrical pulses to the crystal. The crystals here will vibrate, and this vibration as a sound energy will travel through the tissue. Okay, and we'll find the interfaces with differences, with different acoustic impedances. They will generate echoes, and these echoes will be will make the crystals vibrate and transform sound energy to electrical pulses that will travel through this cable to the image processor to form the image at the monitor. This is another kind of transducer that works in the same way. The crystals are here. This is a sectorial, sorry, it's a convex transducer. And the electrical pulses are generated here. They make the crystals vibrate. This vibration travels through the body of the animal, and the echoes come back and are recognized or make these crystals vibrate, which generate electrical pulses that will be transmitted to a monitor that can be your cellular or tablet, and this monitor will interpret the image generated here as electrical pulses. Okay, so here we have a real image of ultrasound. We have to take into account that the transducer touches the skin of the animal at the abdominal wall. So the first band here that we see that is almost white, it's a gray, a brighter gray here. So it means that it is very dense. And I would ask you, what is this band? It's the skin, okay? A little distant here, we have another band that here has a little darker grayscale. What would be this? So I suppose that here we have more water than we have here. It's the blood flowing here. So it's the muscle of the abdominal wall. Here we have another density, a little darker grayscale, and it represents the uterus. And the uterus folds in the abdominal wall that we see. That is a gray that is a little darker comparing to the muscle of the abdominal wall. Also, we have here sorry. Also, we have here a brighter line that represents the bladder wall. And inside the bladder, we have urine. Urine is almost like water. So we can see that it is completely dark, almost like water. And then here we have a brighter surface that represents the large intestine wall. And how it is so bright? Because usually there is air inside of these intestines. And then when we put it all together, we can see the limits of these tissues, okay? And we can see that inside the uterus, we could find a collection of fluid. What would be this collection of fluid inside the uterus, in the uterine horns, if this cell is being examined 18 days after insemination? We consider this the amniotic fluid. So this cell is pregnant. But the important thing to notice here is how the echoes comes back to the transducer are interpreted by an image processor in different energy amounts or intensity that are coming back to the transducer and transform it in an image. And if we have the anatomical knowledge of the body, we can understand this image. Okay, so let's continue. To have another example of image formation, we will use this scheme where we have a draw of a uterine horn of a mare and a linear transducer in relation to this uterine horn, how it is positioned. So here we have the transducer positioned in the rectal wall. Here we have the uterine wall. Here we have the allantoic fluid. Here we have the amnion, the embryo, and the umbilical cord. How is the image that is showed to us in a ultrasound equipment? That is a real ultrasound image that represents this image. So here we have the uterine wall. This is a old-fashioned machine, so the resolution of the image is not so good. Here we have the allantoic fluid. Here we have the embryo. It's not possible to detect the amnion membrane here, but it's possible to detect the umbilical cord here. And to get this image, we call it a section. This is a cross section of a uterine horn with embryonic vesicle inside. Why we call it a section or a cut? Because the ultrasound image will give you 2 dimensions, the depth and the width. Okay, so to get this image, here we have the structure that was examined, And we have here left uterine horn and right uterine horn. Here we have the embryonic vesicle. And to get this image, to make this cut or this section, how the transducer can be must be positioned. This is how the transducer have to be positioned to get this image. It's a cross section. Okay. When we move the transducer in these directions, we can have several cuts or sections of the uterus and the ovary as well. And we will mount a three-dimensional image in our brains. Okay, that's why it's so important to know the anatomical these structures inside the animal. Okay. Well, let's learn a little bit more about sound wave emission. Here we have a 3 megahertz probe, and here we have the cycle of the sound wave propagation. Here we have the compression areas. Here we have the rarefaction areas. And from a compression area to another compression area, we have a wave length. So the wavelength of a 3 megahertz probe is 0.51 millimeters. When we have a 7.5 megahertz transducer, we have a 0.21 millimeters wavelength. As you can see here, it's easy to understand because it's 1 cycle per second. So if I have 3 million hertz, I have 3 million cycles. That is this per second. And if I have 7.5 megahertz, the wavelength has to be smaller to fit in the same second. Why do we have to understand this? When a transducer is working to do the examination, we have the time A, and the time A is the time that the sound is emitted through the tissue. The time B is when the sound pulse, that sound pulse has 2 or 3 wavelengths here. And then when the pulses meets the first interface, we have a reflection of the some part of the sound, and it goes back to the transducer as an echo. So the transducer or the machine will calculate this distance. This is time B. And part of the sound continue traveling through the tissue until meets the interface 2. When it happens, part of the sound will be reflected, and the sound will come back as an echo to the transducer, and the transducer will calculate this distance. Okay? Time A, time B, and time C. So it will give us the axial resolution. Axial resolution refers to the minimum distance between 2 reflectors in the axis parallel to the propagation of sound, that is this axis, which allows its differentiation. For example, to understand it better, let's suppose that in a given tissue that we are going to examine, there's a cyst. This cyst has 0.5 in diameter. What frequency would be the best frequency to see, to examine this cyst? So here we have the transducer, the frequency of the transducer, the wavelengths, the pulse lengths, and the maximum axial resolution. In a 3 megahertz transducer, we will have a wavelength of 0.51 millimeters that will give us a pulse length of 1.53 millimeters and consequently a maximum axial resolution of 0.765 millimeter. And in 7.5 megahertz frequency, we will have a pulse length of 0.63 millimeters that will give us a maximum axial resolution of 0.315 millimeters. So if we use a frequency of 3 megahertz, we cannot differentiate the two interfaces representing the cystic walls, the closer wall and the second wall here. But because the maximum axial resolution is higher or is greater than the diameter of the cysts. But if we use a 7.5 megahertz with a maximum axial resolution of 0.315 millimeters, we are going to we will be able to see the cyst completely, because we can differentiate both walls of the cysts. Okay, it's explain us a concept is the higher the frequency, the better the resolution, and the lower the penetration. It means that if I want to see an ovary in a sow by a transcutaneous examination, I have to use a high frequency like 7.5 megahertz, and I have to put the transducer as close as possible to the ovary. Pressing the abdominal wall to decrease the distance between the transducer and the ovary of the sow. And I have to know exactly the position of the ovary to get there with the transducer. But if I want to make measures of the fetus, I have to use a lower frequency, because the lower the frequency, the worse the resolution and the greater the penetration. So I have to make the fetus to fit in the image square, you know. And if I'm doing the measure of this fetus, I don't have to be very precise according to the structures or the small structures. Okay, so let's interpret this image here. You already know the position of the transducer is the same of the last time we interpret an image in this presentation here. So I suppose that this structure are not so are similar, are familiar for you, and you already know that this transducer is pointed to the flank of the sow, touching the abdominal wall. So you already know these structures, but we are seeing an amount of fluid inside the uterus, the uterine horn. Here we can see the uterine wall and the limits of this wall here. Here we can see a curve of a uterine horn here. We cannot see fluid here inside, but here we know that we are inside the uterine horn and there is fluid inside. If we consider that this sow was inseminated 20 days ago, we will probably give the diagnostic of gestation. This is a gestation sow. So here we have the limit of the abdominal wall and the uterus. Here we have the fluid, allantoic fluid, and here in a brighter color we have the intestine wall. Another image. In this image, we can recognize the intestine wall, the uterus, the abdominal wall, and fluid inside the uterus, but not only fluid, but also a small piece of tissue here that we cannot define considering only this part of the image. But knowing that this sow was inseminated 23 days ago, we can suppose that it is fluid, allantoic fluid. This is the umbilical cord, and this is the embryo. So, interpreting the image here, we can see the intestine wall here. We can see the uterus here, abdominal wall here. The cross section of the uterus with an embryonic vesicle here. And it's not fetus, it's embryo, because at 23 days of age, we consider it embryo and not fetus. It's going to be considered fetus after 35 days of gestation. And here we have the image that we see here. It's a swine embryo, but it's not easy to see the structures, and we will use an image of a bovine embryo in the same age or the same representation stage of development. And here we can see the embryo, the cut section, the cross section was made here. Okay. And here we have the umbilical cord, almost like this, the transducer position to get this section here. Well, so let's talk a little bit about pregnancy diagnosis. We can diagnose estrus detection, pregnancy by estrus detection. I think you all know this. So around 20 days after insemination, if the sow shows estrus, we can suppose that it's not pregnant and it's going to be inseminated again. Physical examination, it's a sign of pregnancy, but the problem is that it is not early, a precocious diagnosis. We can only notice an increase of abdominal distension and the other development in the third part of the gestation, in the final part of gestation. and we can know as soon as we must know as soon as possible that the sow is not pregnant, to inseminate this sow again, and to decrease the non-productive days. Estrus detection is not so accurate because not all cells that are empty will show estrus, or if they show estrus, it cannot be detected by the estrus detectors. Well, hormonal dosage, it's not practical. We can dose, for example, estrone sulfate that start being secreted around day 14 of gestation, but it's not practical. The uterine artery palpation, well, it's not so early because we can see some change from the post-to fremito on day 60 of gestation or a little later. So besides it's not practical, it's not precocious as well. In ultrasound, we have 3 techniques of ultrasound to detect pregnancy. We have the Doppler, the ultrasound Doppler. It's a kind of sound amplifier that amplifies sounds like uterine artery fremitum, or fetus movement, or fetus heart beating, but it's not so early. Okay, we will have a good result or accuracy to diagnose gestation over day 60 of gestation. The mode A, that is one dimension technique, and it will go into it's going to tell us about the amount of fluid that has inside of the abdominal wall, or sorry, the abdominal cavity. So you can imagine that if the sow is with the full bladder, the technique can tell us that the sow is pregnant, but truly it's not pregnant. In the mode B, that give us an image, a picture, okay? You are looking through the abdominal wall to see the structures that will represent a gestation. So is the technique that has the higher accuracy in a earlier age. Here, just to show you what I suppose you already know, that is estrus observation and estrus behavior in open place that is not so usual in Brazil. Most of our production are in the inside production, indoor production. So you have to mount over the sow to see if it's has the standing reflex that is represented here, but we won't not waste a lot of time with this. This is me 30 years ago. And here we are mimicking the movements of the boar, touching the sow to stimulate the behavior of estrus, the standing reflex. Another situation that is the most common situation in Brazil is to detect the estrus in cages, the sows in cages. We cannot let them show the completely behavior of mounting or to accept the mounting of another sow, but we can diagnose estrus. The problem is that when the sows are weaned, we check the sows for estrus every day. And you don't do this usually after 21 days of gestation. You used to do, but it's not so precise. We have to ask people to do that in a good way, you know. Here we have a table showing the sensitivity and specificity, just to let you know. Sensitivity is the ability to correctly detect pregnant females. So when I say that they are pregnant, I will assert, I will be correct in a percentage of the cases. Specificity is the ability to correctly detect empty females. I mean, when I say it's empty, I will be right in a percentage of them. And accuracy is the ability to correctly detect pregnant and empty females anyway. Okay, is what precises the result of that technique will give me. So it's an old table, and I don't think that sensitivity of the estrus observation method is only 50%, not the specificity. With the Doppler, it depends on the age of gestation. I would say that with 60 days of gestation, it's right. It's both right, you know. Mode A, with more than 50 days of gestation, I would say that it's correct. It's also. And the mode B, I would say, with considering our results that I will show you, it's we can reach these results and even more than these results with 19 days of gestation, 20 days of gestation. So it's just an example of a MODI machine. When we touch the abdominal wall of the sows with this probe, you press a button here, and it's going to signalize a pregnancy with one kind of sow, and an empty sow is another kind of sow. It's another model, but both are the same results. And here we have ultrasonography that you already seen something. So the portability of this apparatus is very, very important for the diagnosis. Okay. Here we have an image that an old machine. We can see that the image is not, the resolution is not so good, but we can see the uterine horns here. Okay, the abdominal wall here, and we cannot see any amount of fluid inside. Here we have a good image example, and we can see the difference in the resolution of this machine. So look at the difference, how we can differentiate the intestine from the uterus, right? So here is an empty cell, according to this examination. Just for you to know, see that it's 21 days. And with 21 days of gestation, with this technique, we can be completely sure of the result, empty or pregnant. Here we have another image, and you can see the references we have, that is bladder and uterine walls. What is in this position is all uterine horns. Another machine, and here we have an example of what would be 18 days gestation. So we can see here the uterine horn and a very small collection of fluid with 18 days. Okay, you tell me it's very difficult to find. Yes, it is. But if I'm not sure, you see, with 18 days, we have around 60% of sensitivity. So if I am not sure and I am considering 18 days of gestation, I just don't use this result, because I can be wrong around 40% of the times, 40% of the diagnosis. Okay, but it's just to show you what is the image of a gestation of 18 days. Here we have a 19 days physical that we see here. It's still different, okay, but it's a little bigger than the other. And here we have another example of a 19 days gestation. You can see that the vesicle here is greater than the other image. So what we can say here, usually all the papers, all the experiments use the first day of estrus to determine gestation age. And we know that the cell can ovulate in the first day of detected estrus, the second day, and also the third day of detected estrus. So when I compare these images, I cannot say the exactly days with more than 24 hours of precision, for example. So perhaps this sow ovulated on the first day of estrus, and this sow ovulated in the first day of estrus, and this sow ovulated in the third day of estrus. And that could explain the difference in the size of the vesicles, okay? And here we have a pregnancy image of 23 days. When we compare this image with this image that is 21 days, it's clear that this sow is not pregnant and this sow is pregnant. Do you know what I mean? Here we have a video that I'm going to show you. In this video, we can see the intestine wall here. We can see the uterus here, and we are trying to make a gestation diagnosis. This sow is 18 days after insemination. We are looking for some vesicles here. We are not sure if they are here or not. But one thing that can make some confusion is this kind of cyst, this amount of liquid that will show up here. It's here. It's going to show up here. You see that seems that the sow is pregnant because of this amount of fluid that shows here. So here it's going to show up. Here you can see. Here we have the bladder. It's not bladder, it's bladder. So one could say, well, it's inside the uterus. It can be, for example, it's not so usual, so common in sows, but it can be endometrial cyst, endometrial cyst. Okay, it's not usual. But if I am not sure about the diagnosis, that it's a confusing diagnosis, I just can say I have to examine this sow again. Next time I come here, or if the machine is here and the vet works only in that heart, he can examine the sow in the next day, and the picture will be different. Okay, so let's see another movie here. Abdominal wall, uterus, intestine wall. So here we can see the small collection of fluid inside the uterus. It is 17 days after insemination. And you can see the small collections of fluid here. Well, 17 days. It's a good age to give the diagnosis. No, this is one of the reasons, and this video was recorded in our experiment, and we are not sure about the situation of this sow. We couldn't say it was not pregnant, even seeing some collection of fluid inside the uterus. It can happen with sows that return into estrus because they have more mucus inside the uterus. Okay, so let's see. Another one. So here is the uterus, and here we can see a collection of fluid. 18 days. Here it's going, oh, here. You can see. Okay, let's go to another one. Look here, a vesicle. It's 19 days. Look at this vesicle that is going to show up here. Here another one, here another one. And you can see that at 19 days there are several vesicles. Okay, each vesicle in each conceptus. Another video, it's a 19 days, but it's so fast video. So you can see the vesicles here. You can see the here. All right. Another one. Very, very fastly, but we can define the vesicles here. Okay. another video here. It's 25 days. Look at the, notice the size of the vesicles. I cannot say that the sow is not pregnant. And also you can see there is an embryo that is going to show up here. Here. It's not so clear. Okay. Another video. Here we have an 80 days gestation. So we are going to see the cross section of the fetus. And here we are going to see the heart beating and the chambers, the heart chambers here. If you pay attention here, you can see it beating and you can differentiate the heart chambers. Well, usually we keep doing this examination. It's so rapid to do, as you are going to see.
Thank you very much, Carlos Henrique. It was an excellent insight into ultrasound basics in swine. And this is the end of our part 1 of the presentation. So please visit our website to learn more about ultrasound in farm animals. And if you have any questions, please email us hello@imv-imaging.com. Thank you very much.
Thank you all.